To kick this session off, we have Sergey Tulyakov, who I'm very excited to introduce. Sergey is a lead research scientist at Snap, where he also heads the Creative Vision team. He's done a fantastic set of work on using AI and generative adversarial networks for editing and content creation across images, videos, 3D, and a whole spectrum of other visual media. So excited to hear from you, Sergey. So take it away. Thank you.
Hi, do you hear me well? All right.
Yes.
Yeah, I'm also very excited to be here today, and somehow it's lunchtime, so I wanted to make content a little bit more entertaining, but I realized that for many people it's actually not lunchtime, and then I guess this session will be recorded and transmitted again, so for them it might be one different time. So anyway, so thanks for a great introduction, and I will talk today about image outpainting, and we would focus on diverse and high quality image outpainting. So let's dive in. So what is image outpainting? So given an image like that, for example, we would like to arbitrarily extend it to along the two dimensions, such as here and here. And there are several key features such extension should conform to. One feature is that it should not be just a straightforward copy of or expansion of the content that is in the source image. And second, it should not contain any seams or otherwise visible extension artifacts. So there are several works that try to address this problem via image-to-image based formulation. Indeed, you could take your an image, a big image that you have, and you could mask some part of this image. Then you can use the original image as the target, and you could learn the transformation or extension using a convolutional neural network in a image-to-image based manner. So what's the problem? What's the problem with such formulation? So first, the main problem is that image-to-image translation methods they learn a conditional distribution of the target given the source, and in this task, this conditional distribution and this problem in this framed in this way may be actually bad. Because as you can see here, that the extension is, let's say, just a straightforward extension of the pixels on the boundary. So the network did not generate new content or did not generate that could have been there. It just extended the boundary. In this work, we see that we can change the structure a little bit, but overall the extension is not so interesting. So it's basically some extension of the boundary. And here comes the first work that I wanted to talk about today. So it's maybe some of you had a In-and-Out for lunch. So In-and-Out actually here means that we perform outpainting, which is out, with inversion, which is in, and so therefore we do in and out. And in this work, we're focused on diverse image outpainting. Before we dig into this work, I wanted to introduce this work. Maybe some of you have read this interesting paper, which is a COCOGAN. Basically what they do here, they try to generate images by patches. So how to do that? So we sample some latent, then we can specially extend this latent, and we can augment each latent with coordinate conditioning. For example, this augmented vector will generate this patch. So we keep the same vector, the same latent, but augment it with a different conditioning and generate another patch. And we can concatenate all these patches and pass through a discriminator and train in the usual adversarial setting. So now imagine that we have a model like that, and let's say we have this patch and we want to outpaint the rest. So if we could only get back and invert this patch to this latent code, the outpainting process could have looked like we just extend this latent arbitrarily in spatially and add the proper conditioning, and we can generate a larger image. So I think now we are ready to look into our method. So we indeed would like to leverage the learned unconditional distribution of patches. And as we saw, the conditional distribution for such problem might be not desired. And we want to have diverse outpaintings. So how to do it? So imagine we have a coordinate conditioning generator. So we explore this latent space, and we via GAN inversion. This is basically optimization-based inversion. So we can explore the latent space and find some area in that latent space that corresponds to meaningful extensions of that patch. And we would like to find such latents that first reconstruct well the existing patch, and second, that they produce meaningful extension. And this is how we can perform extension. There are two settings here. One is categorical, one is non-categorical, the other one is categorical. Categorical is on the right, non-categorical is on the left. And we'll look through the non-categorical first. So in a similar way as we saw in the CocoGAN, we sample a latent, we can project it to the W space and spatially replicate this W space, augment it with coordinate conditioning, generate each patch separately, concatenate, and then we can train a discriminator. So we have a patch-based generator. So now when we have this patch-based generator, we can actually perform inversion. So we use a standard optimization-based method for GAN inversion. And in addition to L1 and perception losses so that the reconstruction works well, we had also a prior loss on this Gaussianized latent space. So we computed the training statistics of W and make sure that the Gaussianized W is this one, lies in this, conforms to that statistics. Additionally, we applied the mode-seeking loss, which worked well for many image-to-image tasks. And as I mentioned before, we would like to have diverse image outpainting results. And how to enforce diversity here in this problem, where we actually perform inversion by optimization. So we do it in a way that we sample multiple starting points for optimization, and we, as the optimization converges, we'd like the found W's to be different. So we want them to be dissimilar. We want the reconstruction task to be still done well, but we want the W's be different. So in this way, we could sample different W's and we could generate diverse outpaintings. And now the categorical setting. In the categorical setting, the major difference is that now we have categories for each patch. Categories are one-hot vectors that are, for example, more grass, more water, stuff like that. And we have, again, a Z, we project it using the projection network, and then we combine categorical and non-categorical variables together. And the rest of the framework stays the same. So here, combination of categorical, non-categorical. And then additionally to the discriminator, with additional classification laws that the discriminator tries to tell which labels were used to generate this patch. And this is done in a similar way. It's done in the InfoGAN paper, in which they would like to enforce that the generator doesn't skip those inputs. Optimization is performed similarly. We again take the reconstruction, they use the reconstruction and other losses. But when we do outpainting, we further provide the categorical labels for the patches that we want to synthesize. These are the categorical labels. So let's see some results. So this is the input image, and these are diverse outpainting results. So we can see here that they are realistic. There are no obvious artifacts on the boundary. They're diverse. So for example, you can see that there is a wave which is not present anywhere else. So there is more rock. There is a stone here, and it's similarly for every other outpainting result. So it's not just a straightforward copy of the content because we didn't have this conditional context and outpaint in a generative way. So then we can also outpaint churches. We could generate diverse towers. We can generate 2, 3 towers that are diverse. And I also would like to show here the importance of prior regularization. So if you remember, we have a reconstruction loss to perform the inversion, but if we focus only on the reconstruction loss, the optimization overfits to reconstruction task, and basically the outpainted regions, they look like the original input image. So it overfits to that task and doesn't consider the outpainting task. But if we compute the prior loss, if we add the prior loss, we see that the boundary disappears and this no longer happens. So you can see that it's much better here. Then finally, we could do outpainting into different directions. We could even support irregular boundaries and stuff like that. And I would also like to show some categorical outpainting results. So we could invert this patch and then categorically extend it to, for example, have more waterfall, more sand, more rock. We could ask to add a tower or a tree here, or like a mountain. So we indeed have some control. If we perform the process several times, we can create longer panoramas. And here, what we do, we take a patch, we generate another patch, then we invert this patch, and so on. So this process is a little bit time consuming. And another implementation detail I would like to share here is that we, so as we do this panorama generation, there could be some boundaries, like some boundary as you see here. So to avoid this or to make them less pronounced, what we do, we generate a patch in between. So since we have coordinate conditioning, we can generate, let's say, this patch and also a patch in between, and we can blend all 3 patches. And in this way, we get rid of these boundary artifacts. But so these are interesting results, but this idea that we need every time to invert and we cannot generate infinite panorama and there are some boundaries actually led us to consider a more fundamental problem, which I'm going to talk about in a minute. So before we get back to image outpainting, we will look at a different way of generating images, and then we get back to image outpainting again. So I would also like to present the infinity gun work. And as you can imagine from the title, it can generate infinite images. And so let's see how it works. So another motivation for this work is that the data that we see in datasets is usually very cropped. It's we don't see large panoramas. This data is very hard to get, and I guess if we filter the datasets and require the images to have high resolution be large, we will end up with few images. So the question that we'd like to address is, can we use these observations and maybe even smaller ones to generate images like that? And obviously these are real images. Again, so let's get back to the idea of the COCO again. And as I recall, that there is a common joint of like a global latent that is then specially extended and augmented by the conditioning, and we could generate image patch at a time. So technically we could augment, especially even beyond what we learned. And this way we could generate a larger image. The discriminator, however, still needs to use a large image to be trained on, and we will see in later slides that it doesn't work so well. But this is an interesting idea that we decided to explore further. So what is Infinity GAN? So Infinity GAN is a patch-based generative network where the discriminator and the generator are both patch-based. So we can synthesize very large resolution images, one image at a time by parts independently, seamlessly, and with very low memory requirements. For example, all the results that I'm going to show, the models were used to generate them were trained on one Titan X and also tested on one Titan X. So the generator consists of two parts. One is structure synthesizer, one is texture synthesizer. And we have a global latent. We assume that the whole image has some global holistic appearance that can be modeled by the global latent. This global latent is passed to both structure synthesizer and texture synthesizer. And the structure synthesizer is implemented as an implicit function. So we can query structures at any point in space. And for every point, for every queried point, we can sample a different local latent. And local latent is sampled as a Gaussian, from a Gaussian distribution. So given this local latents, coordinates, the structure synthesizer can generate local structures. Again, so they're independent. And then the texture synthesizer can generate small patches. And we can query the implicit function and we can generate the local coordinate, the local latents as much as we want. So we can spatially extend them as much as we want. So therefore we can generate actually very large and infinite resolution images. And one thing I wanted to share here is a couple of words about the coordinates. So we see an image like that was generated by this approach. And imagine we want to generate the patch here at this location. So we can see that that here vertically the pixels progress from the rock to some water, then there is some mountain, skyline, and then there is sky. And that's true for every vertical row of pixels. It goes from, let's say, grass, water, rock to the sky. So it saturates at both ends. And therefore, we model it with tan H. So we want, again, so it also want to saturate it at both ends. If we look at the horizontal dimension, we see that there is rock, then there is water, then there is again rock, then there is again water. And this happens with different periods. So you cannot actually say what will be the progression along the X direction. But what you can say for sure that the patterns will repeat. And therefore, we path it through periodic functions. And therefore, the coordinates are modeled like this triple tan and cosine and sine. For models for images that don't have this bias, like that for images maybe like satellite images, it can be modeled differently. Okay, so the discriminator is trained using real patches. Oh, it's generated patches and also real patches. And additionally, we want the discriminator to be able to tell what is the vertical location of the patch. So we have this auxiliary loss that tells us what's the vertical location of the patch. All right, so with the shared global variable, the coordinate system that we just seen, we can generate a number of patches. We can then arrange them spatially, and we can sample diverse local variables and generate the rest of the image. And this is an example of the image generated by our method. Another interesting application is that what we call style fusion. For example, we have two global latents. We generate patches for the first and then for the second. We can specially arrange them and query images at the remaining locations. And this is the result. So here you can see clearly on the left, it is more like greenery and more sunny. On the right, it's more like a sunset type of colors and more dark. And there is no clear boundary, and the boundary is very smooth. And this is an image generated with the model that was trained on that big patches, 100 by 100. And the image is 2000 by 1000. We can then zoom in to see local structure in detail. So we also want to compare to existing baselines. There are not so many, but we do our best. So we first confirm that all those baselines, Kokogan, Singan, can generate decent images at the training resolution. So here, for example, the baseline for StyleGAN and CI means non-constant input, which means that we extend specially the constant input of the StyleGAN. And if we now generate images larger than the training resolution, so for Kokogan it doesn't work. For Singan and StyleGAN, we see repetitive textures, so also doesn't really work. And for InfinityGAN, it generates interesting results. Another thing I wanted to share is that we use structure and texture disentangled sampling. For example, here you can see that the structure is different, but the style is fixed. It's some sort of greenish landscape. We then fix the structure, and in every column we have different structure. So in every column we have fixed structure, but in every row we have fixed style. And we can see that like a grass field can become a prairie or a desert. So basically the semantics stays while only the texture changes. These are some of the more recent results that we've got. We generated 2000 by 2000 images, and these models were trained on larger patches. And also we could generate 256 by 10K. If you concatenate all these rows, you can generate really long panorama images. All right, so that was a detour. Let's get back to the image outpainting stuff. We can take the real patch and we can invert it using the framework proposed in the In&Out, and we could get back to the global and the local latents. And then outpainting would just mean that we want to extend the local latent specially, and we can do it in the many diverse ways, no boundaries, because of the nature of the method. We don't need to perform any optimization. We just do it once, and so the diversity is actually something that happens at no cost in this method. So you can see 4 diverse outpainting results. If we compare with other methods, we can see that there are boundaries. So here in the previous slides that I showed In&Out, I didn't show boundaries, but I said that we generated patch in between and did blending. So here we just show the output of the network and don't do any post-processing. And for In&Out, there are no such artifacts. And I would like to share a couple of more applications of this work. So for example, you have a real image A and a real image B, and with the InfinityGAN, you can generate everything in between, which we call image in betweening. You can generate arbitrary length in betweening. You can even in between the same image, so you could have both images be equal. And you could do it for arbitrary lengths, and you could have cyclic panoramas, such as here. So in the summary, we discussed two works. One did outpainting inversion, and it was a diverse outpainting method, and it took advantage of unconditional distribution. The other one, first we introduced a new method for image generation and then applied it to image outpainting. And due to the nature of the method, image outpainting was easier to achieve and was seamless. So I think this is last slide. And I'm happy to take questions if time allows. And that's it from me.
Sure. Thank you, Sergey. So thank you. That was a great talk. And I invite the audience to post questions in the Zoom chat, and we'll relay them over to Sergey. So I'll start off with the first question from here. So one question is, would this work for more structured scenes such as indoor scenes?
For indoors, we haven't tried. We have tried for something like cities and town skyline. It works, but it's a little bit less meaningful. So we're working currently on making it work. So I think it's decent, but we would want to improve quality slightly.
The next question is, actually, there's a comment that says that this is lovely imagery. And the question is there a way to combine this with semantic editing systems to provide more user control?
I think so, yeah. So we focused on unconditional, let's say, image generation and not eye to eye. I think we could, well, someone could publish a paper on infinite eye to eye or something like that. I think that would be really good to read.
Oh, I think we have time for, okay, another question. Great talk. Once the model is trained, do you use any quantitative metrics to evaluate the quality of the results of outpainting images to pick the best, or do you use subjective evaluation? We
use both. So there are not many metrics to perform evaluation. So there are both papers are available on arXiv, and we use diversity scores. We use FID. Sometimes we can compute the reconstruction because we know the rest of the image. So there are a lot of evaluations which I skipped in this presentation that we performed in the papers, in both of them.
Awesome. All right. So last question. For maintaining continuity, is the local latent variable continuous in the coordinate space?
It is. No, so the local variable is sampled per patch. So there are differences. It's not interpolated.
I see. Okay. Cool. Awesome. Thank you so much, Sergey, for that great talk. Maybe we can do a round of applause.
Thanks for having me.